Good morning to all of you, distinguished panelists, all the participants and delegates. It's a pleasure for me to be with you this morning for the session relating to farm and ecosystem level benefits of CA for farmers, for society, and for environment. Much has been talked about right from the first day when the inaugural session was held, and Director General of FAO, Dr. Q, had made an impressive speech relating to importance of conservation agriculture, followed by the inaugural address by Dr. Amir Qasim. So I don't have to really talk much about importance of conservation agriculture as it relates to present context very clearly when we are facing the COVID pandemic. Realization could have been not more than now with regard to conservation of natural resources and having agriculture more sustainable for the benefit to not only farmer but to society and for our environment. And in this respect, we have today in this session, which is relating to sub-theme 2, and 7 presenters. All presenters would be making brief statements of about 10 minutes each. There are 4 recorded and 3 will be presented by our participants themselves. So rather than taking more of time, because let me also briefly mention some housekeeping issues that we will take up the discussion at the end after all 7 presentations are over, and you would kindly note down a specific question, and if you have any specific issue to be raised, you can also indicate it in the chat box or during the discussion time, raise your hand. We will see that there is opportunity for as many participants possible in the given time. And secondly, my request to all speakers is to kindly remain confined to the allotted time of 10 minutes each, so that we do have an opportunity for participants to also either seek clarification or raise questions for your intervention at the end. So with this, the first speaker is Dr. Ahana Dey. She's a research fellow at one of the important state agricultural universities in West Bengal. Her area of expertise is micronutrient studies in soil plant systems. She is currently working as a senior research fellow in a project, and she has also had some exposure of working at Kansas State University, Manhattan, USA. I would now request her to kindly take the floor.
Thank you so much, sir. I have already sent my recorded video, so I will kindly request you to play the video and see you in question answer session. Thanks a lot.
Hello everyone, hope all of you are doing well. Now I am going to share my screen. Okay, so a very good morning to all of you. I am Ahana Dey, currently pursuing my PhD from Bidhan Chandra Krishi Vishwavidyalaya, West Bengal, India. from the Department of Agricultural Chemistry and Soil Science and under the project Center for Advanced Agricultural Science and Technology on Conservation Agriculture. The topic of my presentation is Initial Impact of Conservation Agriculture on Soil Fertility. Now coming to the introduction. As we all know, conservation agriculture has its own benefits both in terms of resource conservation and energy conservation. And in recent days, it's coming strongly in India too. Till date, in India, conservation agriculture has been expanded to 1.5 million hectares of the land. Conservation agriculture practices improve soil physical, chemical, and biological properties in long-term basis. However, its performance during the initial years of adaptation is debatable. Declining soil fertility is proposed to be one of the reasons for such uncertainties. Those things keeping into the mind, we have set certain objectives of our work, and these are to study how do conservation agriculture practices of different intensity with different cropping systems affect soil fertility in initial years, and secondly, to find the impact of such changes in soil fertility on the nutrition of crops. Now, this is our experimental details. We have started setting up of the conservation agriculture field from the year of 2018 in our university research farm, Vidhan Chandra Krishi Vishwavidyalaya, West Bengal, India. Here the soil type is clay loam under the soil order insectisol. And here we are working with three main rice-based cropping systems which are popular in our locality. And those are rice, wheat, rice, cauliflower, and the rice potato. We have taken tillage as the main treatment, and three different tillage practices are the conventional tillage, reduced tillage, and zero tillage. And as sub-treatment, we have taken the combination of the residue and the nutrient, and those are no residue with 100% NPK, 50% residue with 75% of NPK, 50% residue with 100% NPK, 100% residue with 50% NPK, and 100% residue with 75% of NPK. And here as a residue, we have used rice residue. Now coming to the result part. Now, effect of CA on soil pH with the different cropping systems. So, if we consider the impact of soil tillage effect, in the initial year, it won't affect it too much in the soil pH. But if we consider the effect of residue and nutrient combination, we can see with the increase in the level of the addition of the residue, there is an increasing trend in the pH in the initial year of the conservation agriculture. But if we consider conservation agriculture practices as a whole, so here you can see with the increase in the level of intensity of CA, there is no such a big impact in the change in the pH has been observed. Now coming to the effect of CA on the organic carbon. Here we can see with the increase in the level of the intensity of CA, there is a declining trend in the soil organic carbon in the initial year of conservation agriculture practices. Now coming to the soil available nitrogen. Here with the increase in the intensity of the conservation agriculture practices, there is a declining in the trend in the soil nitrogen has been observed, and many of the treatment has been recorded below critical limit, which is 240 kg nitrogen per hectare. But if we compare the sole effect of the tillage and the residue and nutrient combination, so we can see in the initial year of conservation agriculture practices, the impact of residue and nutrient combination is much more on the soil available nitrogen over the tillage practices. Now coming to the effect on the available P. Here we did the Olsen phosphorus as our initial soil pH is found in the alkaline range. So in the system rice, both the rice wheat and the rice cauliflower system, the Olsen P show a slight increasing trend over the increase in the intensity of the conservation agriculture, while in the rice potato system, there is a slight declining in the trend has been recorded in the initial year of practices, and all the treatment has been recorded on the above critical limit. Now coming to the available potassium content. So here we can see in both the rice wheat and the rice potato system, the available soil potassium is near to the critical limit of the soil. But in the rice cauliflower system, there is a soil containing a good amount of available potassium. But in all, irrespective of the all cropping system, with the increase in the intensity of the conservation agriculture, there is a declining in trend in the available potassium has been observed. The same trend has been observed in the secondary nutrient available sulfur too, in both the cases of the rice, cauliflower and the rice wheat, but exception has been found in the rice potato systems. There is a certain increase in the trend in the available sulfur has been observed with the increased intensity of conservation agriculture. Now coming to the soil micronutrient, that is DTPA zinc has been recorded and certain level of increase in the zinc content with the increased level of intensity of conservation agriculture practices in both the rice wheat and the rice cauliflower system. But exception has been observed in the rice potato system. Here we can see with the increased level of the residue addition, there is certain declining in the soil DTPA zinc has been recorded and some have recorded below critical limit too. Now coming to the DTPA iron content, as compared to the non-CA, with the increase in the intensity of the CA, in the initially there is a certain decline in the trend in the DTPA iron has been observed, but in the higher level of CA, DTPA iron has shown the increasing trend. Now coming to the effect of intensity of CA on yield and the grain quality of the crops. Here we can see with the increased level of intensity of the CA in the initial year of practices, there is a good amount of decline in the yield has been observed. But among the treatments, CT plus 100% residue plus 75% of the NPK out-yielded over others in both the rice wheat and the rice cauliflower system. But in case of the rice potato system, RT plus 100% residue plus 15% NPK has been recorded the highest yield. So here we can see in the initial year of conservation agriculture practices, the effect of residue and nutrient combination is much more prominent in the yield than the effect of the tillage practices. So now, while there is some sacrifice in the yield has been recorded in the initial year of CA practices, but that is it affect our grain quality too. That's why we have checked some grain quality parameters too, that is grain protein percentage and grain phosphorus percentage, and in both the cases we can see along the intensity of the CA in all the system, the grain phosphorus content and grain protein content is above the critical limit. That means it's not hampering the grain quality at all. And again, for the micronutrient content also, though in one or two treatments there is certain decline, but in the other system has recorded above critical limit of the grain zinc and the iron content. Now coming to the conclusion. So as a summary, a declining trend in the organic carbon in soil with intensity of CA practices was observed across the system study. With the intensity, an increasing trend in the soil phosphorus, zinc and iron availability has been recorded, while a decreasing trend in the nitrogen, potassium and sulfur were noted. As yield is declining with the intensity of the CA in the initial year of adaptation, but the CT plus 100% residue plus 75% NPK out-yielded others both in the rice wheat and the rice cauliflower system, while RT plus 100% residue plus 50% NPK under rice potato system. That means residue addition impacts on the yield over the tillage effect. And though yield is hampering, but the nutritional quality of the grain is remaining unhampered. And lastly, the rice cauliflower system is the best in starting years of the adaptation of CA practices under the subtropical climate. That's all. Thank you.
Thank you very much to be in time and to be very succinct with regard to your research work. I appreciate that. Second speaker today we have is Dr. Atef Haddad. He is from International Center for Agriculture Research in Dryland Areas, ICARDA. He graduated from the University of Aleppo in Syria and then worked there as a research scientist and assistant professor, and with ICARDA he has a long experience of almost more than 4 decades and has been promoting conservation agriculture in Central Asia. So rather than taking more of your time, and he had been working in projects which are being funded by UNDP and Aga Khan Foundation. So, Dr. Atef, floor is yours.
Of conservation agriculture adoption in Syria. Conservation agriculture was known in the region from 18th of the past century, but it was effective in the region in 2006 by ICARDA, supported by Australian funds and expertise. It was introduced to the rain-fed agriculture, which is characterized by 200 to 350 millimeters of rain, limited crop cereal legume rotation, but mostly marginal land with continuous barley planting, and it is characterized by crop residues over summer. The successful conservation agriculture, which was practiced after 2006, it was based on 3 issues: conducting an adaptive and applied research, employing participatory extension, and fabrication, which is the most important point, is fabrication of local and cheap, local zero-tillage seeders. We searched for different workshops all over the country to produce seeders. There were 8 workshops were selected. They were provided with technical and financial support. They could produce simple and light zero-tillage seeders with tine type. Of course, this is here. We work together, and they at the end they produced enough seeders for the country, and then later they started to export to neighboring countries. Different versions of those seeds were produced, but mostly they were 2 to 4 meter width, mounted or trailed, fits to 45 to 100 horsepower, available tractor, affordable cost for the local farmer, $800 to $2,500. Zero tillage were freely made available for farmers, communities for the first 2 seasons. There was a good adoption after this campaign, and here the adoption is clear. In a few years, we could reach 30,000 hectares and over 500 farmers in Syria, and of course the adoption spilled over to Iraq. The conservation agriculture work in Syria actually means 2 sectors, which are the orchard part and the irrigated area, irrigated agriculture. Of course, each of them is 1 million hectare, which is it's big area, but implementation is quite difficult for the time being, as orchards require to get associated with the water harvesting and irrigation. We have to move from traditional flooding method into modern agriculture, modern irrigation techniques. Middle East crisis started in 2011. Unfortunately, it has severely affected all Syrian economic sectors, especially agriculture. Farmers lost their assets or displaced. Most funds and subsidies were reallocated from agriculture development into relief activities. Farming became very difficult because of lack of inputs and security. There was a shocking report from FAO in 2016 indicated that the damage caused in Syria for the agricultural sector is $16 billion, half of it for crop production. And under the conflict, some farmers, they noticed that practicing zero tillage is more appropriate or suitable for these stress conditions, as this technology is input saving, like fertilizer and seeds and agrochemicals. So this is an example for a few farmers in different places in the country are practicing conservation agriculture within the conflict. The production of zero-tillage seeders also was affected. The country became disconnected, and there was a big migration of local expertise. Those workshops where they were trained, they left the country, most of them, or we could not approach them. A few new workshops were sourced after 2016 by the support of Aga Khan Foundation and United Nations Program. Workshops were sourced in safe area. They were again trained, tested the seeders together, and started to produce again. This is a picture of a destroyed seeder because of the conflict. Restoration of conservation agriculture was given a priority in the country. Several meetings has happened in Beirut, in Damascus, and so. All recommended that to follow the same procedure of research, extension, and zero-tillage seeders, but with some slight difference in changing the strategy of dissemination of conservation agriculture. And unlike the past, we were providing only a seeder for first-time users. The new strategy suggests that farmer has to be also given the seeder, as well as some other production inputs like quality seeds, fertilizer, and herbicides. Within the conflict, very limited research and development on conservation agriculture was conducted in the country, very little here. And because of the conflict, there are no updated records for the conservation agriculture planted area. International organizations, actually, they tried, as usual, they tried to support in this respect, but they provided small conservation agriculture development projects with limited funds and period. But all of them, United Nations, UNDP, FAO, World Food Program, ACSAD, ICARDA, and Aga Khan Foundation, and this is the National Research Program, all of them, they started to provide seeders to farmers, but they gave less importance to the crop management. And this actually will put the conservation agriculture technology in a risk for the future if it keeps ignoring the proper crop management. If we can conclude key messages at the end, we'll go back to the FAO 2016 report about the recovery recommendation. The first one is adoption of conservation agriculture. The other message that, yes, it is important to provide zero-tillage seeder when we will start adopting conservation agriculture, especially for the first time for the farmer, as it is a big capital for the investment capital. But also it is not enough. providing zero tillage is not enough. It should be associated with a lot of training and follow up with the crop management. The last message is conservation agriculture for orchards and irrigated system is ultimately as important as for rain-fed crop agro system. Thanks to conservation agriculture, that's what this farmer is telling, and he's holding his zero tillage crop in his right hand, and he says again, and I would say thank you to all. Thank
you, Atef, for being in time and for giving an account of initiatives taken on conservation agriculture in Central Asia and West Africa region by ICARDA. We know how the conflict has affected research system adversely, but your presentation is well received. I now go to the next presentation by Dr. Dennis Garrity, a well-known figure who doesn't need any introduction, an old colleague and friend. Nice to see you here, Dennis, after a long time. He's a renowned systems agronomist and former Director General of World Agroforestry Center, where he served for almost 1 decade and led the agroforestry program at a global level. And he had also been the dryland ambassador for UN Convention to combat desertification from 2001 to 2011. So again, a very important role he has played. And he is going to talk about his recent initiative through collaborative efforts with regard to EverGreening the Earth. So rather than taking more time, Dennis, floor is yours.
Thank you, Dr. Paroda. And indeed, it's great to be back with you again today. And good day, colleagues. I'm grateful to have the chance to address you about some key topics that I think are critical to all of us in the CA universe. First, unfortunately, we are in a fight for our lives as global heating continues to accelerate. So I'd like to preface my remarks with the latest science on the state of our climate predicament. And then I want to draw your attention to the role that CA can play in helping to address it, particularly if we think out of the box during these highly unusual times. The rate at which global heating is accelerating.
I address you today to propose that the agroforestry and forestry community put its weight behind a program of research and development on leguminous shrubs to help save the planet from runaway heating.
Sorry. The rate at which global heating is accelerating is absolutely frightening. What the most recent science is telling us is that probably it is much worse than you thought. We will very likely be breaching the 1.5 degrees C Paris target within the next few years. And we may already be above it by 2030, as you can see on this graph, a full decade ahead of the IPCC predictions. There is nothing much that we can do about that now. That can change this trajectory. It's too late for that. So, so apparently, we've lost the battle to stay within 1.5 degrees C. But what about the 2 degrees C Paris target? 2 degrees C is now likely to occur before 2050.
2 degrees C is now likely.
The evidence is mounting that 2 degrees C may be triggering tipping points that will lead to a hothouse Earth scenario of rising temperatures that are out of humanity's control. There are many such tipping points that can contribute to this out of control situation. 9 of them are highlighted on this map. The one that scares me the most is permafrost melt, which would unleash an accelerating torrent of carbon dioxide and methane into the atmosphere. And so we do now need to look at global methane emissions, which are currently accelerating. I chair the board of the Global EverGreening Alliance. The Alliance's mission is to achieve massive impact in land restoration globally. We now have over 50 member organizations, including virtually all of the biggest development and conservation NGOs working around the world, as well as many regional, national, and local organizations, and also key research organizations that provide technical support. It has mobilized its members and partners in the United Nations and in governments throughout the world to implement regional and national restoration programs. We knew that we needed to do more than simply engage in restoration. We needed to spearhead a big, audacious drawdown goal to inspire action at all levels, from the global right down to the individual community. The evidence shows clearly that the enormous potential for nature-based solutions to be a cornerstone of the CO2 drawdown effort. So we added up the streams of realistic possibilities, and we established a goal to be capturing 20 billion tons of additional CO2 from the atmosphere every year by mid-century, while improving livelihoods and caring for the land. That goal is the basis for the EverGreening the Earth Green Up to Cool Down campaign, which was launched at the United Nations a year and a half ago. We are determined to achieve it. This IPCC graph shows the general path to emissions reductions that is essential to achieve net emissions at zero level by mid-century. You'll note the expectation that emissions will continue to increase until 2030 and then must turn drastically downwards thereafter. I've added in the annual absorption of CO2 by the oceans and the land base, which you can see below the line. Together, they are already drawing down about 20 billion tons of CO2 per year, which makes it possible for the world to achieve net zero emissions by about 2040. The imperative is to ramp up the drawdown by vastly increasing the scaling of nature-based solutions that will evergreen the Earth. Such a process could enable us to be in negative emissions territory by mid-century, as shown by the blue zone at the bottom of this graph. Negative emissions will be vital to any attempt to stabilize the global temperature. The campaign's goal is made up of target areas for capturing and storing more carbon in the world's landscapes. We've laid out unique strategies for the ecosystems of farmlands, degraded forest lands, and degraded rangelands. You'll note that one of these targets is increasing soil carbon through the expansion and deepening of conservation agriculture to reach a target of 500 million hectares by 2050, a goal that Professor Amir Kassam reiterated in his keynote address on Monday. This is certainly achievable, given that Professor Kassam has also stated that there are now over 205 million hectares of conservation agriculture in the world, and the rate of expansion is still accelerating at about 10 million hectares per year. So what would be the contribution of conservation agriculture to the overall CO2 drawdown during the next 30 years? Well, the buildup of soil carbon is quite variable across CA systems and zones, and the IPC special report shows that it's generally in the range of about 0.04 to 0.4 tons of carbon per hectare per year. The campaign targeted calculations use the average value of 0.2 tons of carbon per hectare per year, with a target of the expansion to 500 million hectares. This will contribute an additional 370 million tons of CO2 storage in agricultural soils. This is an abatement curve showing the overall effect of the various target areas that would be covered in the EverGreening campaign. Now, if you look at the 6 target areas on the right side of the screen, you'll see that unfortunately the contribution of CA is significant, but somewhat modest compared to the other major options for drawdown. The question is, how can we boost this rate of drawdown by CA to be more consonant with the other opportunities? The key way that I see to do this is to add more useful and productive trees and shrubs to CA farming systems. This can be a huge advantage in further diversifying CA systems and making them more resilient to climate change. It could easily double or triple the carbon drawdown of CA systems compared to conventional CA practices, which have to date mostly ignored the opportunities for agroforestry. Illustrated here is one option that has been scaled up to hundreds of thousands of CA farmers in Zambia over the past decade. The incorporation of 100 acacia albida trees per hectare that greatly boost yields and protect the crops from drought and overheating. Another option is integrating leguminous shrubs into conservation agriculture systems through alley cropping. This practice has been expanding rapidly in Zambia, Malawi, Kenya, and Sri Lanka, among other countries. Obviously, quite different solutions will be required in the more northern temperate climates, but now is the time to launch serious efforts to explore alternatives of CA with trees and shrubs, to vastly increase the potential for soil carbon storage and new ways of increasing farm income, diversifying and reducing costs. We are currently developing a campaign action group on CA to advocate for such farming systems innovations. The action group will advise the campaign on the action plan to reach 500 million hectare target by 2050, with specific milestones working back from mid-century right to the present day. It will develop guidelines on how to optimize carbon capture in CA, particularly through the conversion of CA to CA with trees and shrubs. And it will refine the global analysis of CA carbon benefits due to CA practiced with trees and shrubs. We would love to hear from you if you would be interested in participating in such a group and contributing to its analysis and work. In conclusion, the climate emergency is so dire that fresh new approaches to help overcome it at scale are desperately needed. CA, especially CA with trees, could be an important part of that solution. I urge you to visit the evergreening.org website to read the white paper on the campaign with its section on conservation agriculture, and then do get in touch with me. I'd be delighted to hear from you. And let's make this evergreen world happen. I thank you for listening, and back to you, Raj.
Thank you, Dennis, for a very comprehensive presentation with regard to initiatives that are to incorporate in cropping systems the role of agroforestry. And very rightly, you have pointed out the expected benefits that are likely to be of great relevance in today's context. With this, maybe there will be questions later, but your alliance is important, and more participants could join and take their effective role to contribute to the targets of 2.5 billion ton carbon dioxide, oxygen per year target that you have fixed. I now have the next speaker, Dr. C.M. Parihar. Dr. C.M. Parihar is currently working as a senior scientist at the premier Indian Agriculture Research Institute in New Delhi. His work is mainly relating to the significant contributions for developing, adapting, and scaling conservation agriculture. He is a young, enthusiastic researcher, quite well recognized for his achievements, and he is also contributing in developing CA roadmap for India and has about 65 research papers so far. So again, like Ahana Dey, he is an active researcher on conservation agriculture, particularly in the context of Asian agriculture. So, Parihar, floor is yours.
Sir, sir, good morning, one and all.
Respected Chair, Dr. R.S. Paroda, sir, Dr. Yash, and distinguished participants, good morning, one and all. Myself, Dr. C.M. Parihar, working as Senior Scientist, ICR, IRI, New Delhi, India. I will talk on conservation agriculture can be an option for improving crop and water productivity, that too with lower environmental footprints. As we all know that rice wheat is the dominant cropping system in Western IGP, but during recent past, ill plateau, deterioration of soil health due to continuous puddling in rice crop, residue burning in rice bed systems contributes to the environmental pollution, and declining in water table due to water guzzling nature of rice, as well as some policy like free electricity by some of the states of India further aggravate this problem. All these factors are major cause of concern in rice wheat cropping system. Therefore, in past also the attempt was made to diversify rice with maize, but could not succeed due to non-availability of high-yielding genotypes as well as non-availability of procurement policy of government. But in recent years, Indian maize program and several multinational companies developed high-yielding single-cross hybrid maize genotypes, and government also provided the assured procurement policy for maize. So keeping all these concerns in mind, we have initiated a long-term conservation agriculture experiment under diversified maize-based cropping systems, and we have shown the maize crop during the rainy season, and wheat, mustard, and chickpea and winter maize during the succeeding winter season. And during summer season, after wheat and mustard, we have shown summer mung bean crop, and after chickpea and winter maize, we have shown the Susbania crops. And the result of our 13-year experimentation showed that CA-based sustainable intensification improves the crop and water productivity, as CA-based zero tillage flat and permanent bed plots resulted significantly higher system productivity by 13 to 17% and farm profitability by 22 to 27% as compared to the conventional practices. And across the diversified cropping systems, the system water productivity was maximum with the maize, mustard, mung bean system, which is at par with the maize, chickpea, sesame cropping system. And in all the diversified cropping systems, CA-based permanent bed plots resulted significantly higher system water productivity as compared to the other tillage practices. And if you see this figure below, then it is the yield trend with respect to system productivity of 12 years, and compared with the two cropping systems, that maize, mustard, mung bean and maize, wheat, mung bean systems. Here still there is no yield plateau in both the cropping system, but the interesting the yield gap between conventional as well as the CA practices is widening with the succeeding years, and similarly in the maize, wheat, mung bean cropping system as well. And due to this high yield, we are advancing towards the attaining the potential water productivity, that too with more than 2 and 3 kg of wheat and maize grains per cubic meter of water applied, and through which we can advancing to achieve the potential water productivity. That information we have published in the Agriculture Water Management Journal. And this CA-based practices can maintain the soil moisture under contrasting rainfall events. Yes, our evidence shows that this if we see this field view picture of conventional and conservation agriculture practices, this was taken on 26 September 2019 after heavy rainfall of 124 mm in 2 hours, and after the stop of the rainfall 3 hours after that, if you see there is a complete residue of water in the CA plots, while there is a flooding situation in case of the city plots. And here if you see this graph shows that this dense dots represents that there is a proper distribution of the soil moisture. Here in CA and this CA based PB and JT plots, there is a dense dotted, evenly distributed. But if you see these dots in the CA CT conventional tillage, then there are the scattered dots, and which represents there is a not even or proper distribution of the soil moisture. This information also we had published in the Field Crop Research Journal. And then by higher yield and we are achieving and the nutritional security by sustainable intensification, that we compared in terms of glucose equivalent yield, protein equivalent yield, and ultimately the protein equivalent yield for adults. So if you see the 3 years analysis basis, this pool analysis, then this CA based sustainable intensification can able to feed 10 more adults as compared to the conventional practices. So we can say that we can achieve the nutritional security by this CA based sustainable intensification. This information also we had published in Energy Journal. And this CA based sustainable intensification can also address the climate change issue as well as the lowers the environmental footprints. As we in our investigation we have taken the end-to-end emission pattern in the different seasons and under different tillage practices and cropping systems, and if we see ultimately the total annual N2O emission in CA based practices was about 20% lower as compared to the CT conventional tillage practices, and this information also we had published in Science of the Total Environment Journal. Now, with respect to the soil, particularly the soil organic matter and soil carbon content, the CA-based practices enhance the soil organic carbon content as well as soil and organic matter, which Dr. Ratanlal used to talk about the critical limit of SOM, and then we achieve the critical limits, we can increase our crop productivity by about 40 to 100 kg per hectare megagram of soil organic carbon content. This information also we have analyzed and we have published in Soil Tillage and European Journal of Soil Science Journal. And then this physical property also we have analyzed, we have compared particularly the penetration resistance and bulk density, which are the salient driver factor for the better soil health, and we found that in the soil, particularly the crop root zone, the penetration resistance and both are the lower as compared to the CT in CA, and this also we published in Soil and Tillage Research. And recently we have conducted an experiment at Bisa Farm, Ludhiana, Ladwal, and particularly in rice crop, where we compared this conventional PTR practice with CA alone, that the direct seeded rice under flood irrigation, and CA plus, that is zero till direct seeded rice with subsurface drip irrigation. And interestingly, we can see this yield reduction was there in the CA plus practice, that was about 4.5%, but that too at the cost of 50% lower cumulative water application, and that also reduced 66% of deep drainage and ultimately increased the 47.7% water productivity. And similarly also we conducted the experiment in maize also, but the response was not so much as in case of maize, rice, as maize is lower water requiring, but there was a yield gain of about 20%, and that too with the 11% lower water, and ultimately the water productivity was also 28% higher in CA plus practices in maize as well. And now I want to acknowledge Director ICR-IRI New Delhi, Director ICR-IMR Ludhiana, and Dr. ML Jat, CIMIT India, for their all kind of support, all scientific, technical, contractual and students who are involved in this data collection, data analysis in this project. Thank you one and all.
Thank you, Dr. Parihar, for a good account of various activities relating to rice wheat system and its diversification for sustainability. Much appreciated. Maybe there will be questions during the later part of this session. Now we have the next presentation by Dr. İrfan Gültekin. Dr. İrfan Gültekin is an agronomist and is working at a research institute in Turkey. He is a pioneer of promoting conservation agriculture in his country and conducted several short and long-term experiments relating to wheat-based cropping system. So floor is yours, Dr. İrfan.
Thank you, Dr. Paroda, and also thanks a lot for organizing committee and member of the staff. I will present today the follow is an opinion conservation agricultural under dryland conditions. That's possible or not. I think all of the team members agree with the operating principles behind the CA is the minimize distribution of the soil surface, residue retention and crop rotation. To gain the full benefits of the CA, all the three principles have to be applied at the same time. But on the other hand, growing only the one crop every 2 years and around 15 months without cropping, which is the called fallow. The main idea this period accumulate the water in the soil for the following year's crop. Central Anatolian Plateau in the middle part of the Turkey, the region surrounded by mountains, hot and dry summer, cold and snowy winters. There is frost very common events. The average annual rainfall is less than 400 millimeters. The majority of the soils has less soil organic matter content and high level of lime and potash. In this region, nearly 1/3 of the arable land left or for fallow. Half of the area occupied winter cereals as a wheat and barley. The fallow periods, relatively stable grain yields, less economic risk compared to any other rotations. But the current practice to excessive tillage causes degraded soil, increasing the production cost, and with the climate change make it difficult to maintain. There are several experiments show us CA methods can be successfully applied in the different parts of the Turkey. Need to understand the benefits of CA and what kind of crop rotation give the best results, and appreciated drill and promoting CA. Compared conventional tillage and CA based on the wheat production system. There is 6 different binary crop rotation were tested last 5 years, and each year got data from wheat and the previous crops. The experiment is for replication and each plot size 150 meters. The fallow cereal 2-year crop rotation system has been practiced traditionally for hundreds of years in the region. The first tillage operation starts with the mulberry plowing in March or April. The hot and dry summer, reducing the soil moisture loss is the most important objective. Secondary tillage equipment, multiple shallow passes provide the clean storage or dust mulch, winter cereal plants with the drill in the same period, in the period from mid-September to December, and harvest June or July. On the other hand, no-till seeds directly deposit into the untilled soil, which has retained the previous crop's residue, if necessary, with controlled by glyphosate during the pre-sowing time. There were 5 different existing crop rotation used at the previous crop, and in addition, fallow evaluated. The crop rotation was important determinant of the wheat density. It was highest in the continuous wheat than any other crop rotations. In the experimental area, where the annual precipitation long-term average is 250 millimeters, the average of the last 5 years has remained 250 millimeters. In 2016, the precipitation was just 200 millimeters. Just 1 year, we get more precipitation, but 1/3 of the rain received just in December. That is the winter period. The yield of all prep plants were always higher in CA. Also, CA systems to be better than the conventional tillage for the wheat yield. Crop rotation was a more important determinant of wheat yield than was the tillage system. The highest wheat yield after fallow, and if look at the lantern after wheat yield, closer as a fallow wheat yield average. However, looking at the years one by one, it seems that wheat yields fluctuate after lanterns. Even there has been a year when it was not productive. In addition, seeing that yields remaining at the very low levels in the traditional processing actually shows why the remains preferred fallow. According to partial budget analysis on the yields obtained and the expenditures made, CAS is definitely more economical production model. Conventional tillage causes more expenses and lower profits. It was all observed that the fallow reached the highest value in the production under conventional tillage. However, it has been determined that is the profitable include one of the legumes in the production value collection in the areas where CA is applied. The fact that the amount of water content in the soil is higher in CA plots has an important role in all these results. The result obtained shared with the agricultural machinery manufacturers, and they contributed to the production of the domestic and affordable drills. In order, promoting of CA on farm trails and demonstration studies are carried out. On the conclusion, the conventional tillage, less yield, high amount of production value, small amount of the income, not permitted crop rotations, and degraded soil. However, CA system is the beneficial. CA system significantly increases grain yield, reduce the production cost, save more precipitation for crop production, resilience in timing of field operation, established rapid and reliable crop, more cropping system flexibility. But perhaps the most important critical point, if we take into the account that the farmers take the production year as a basis, regardless of the income table format, according to the long years, in regions with low rainfall, it is suggested that the following is recommended at least in the initial phase. We need to know that it is enable them to the more resistant vulnerabilities that may occur in the first year. Thank you for your attention, and thanks to all of you.
Thank you, Dr. Irfan, for being in time and convincingly demonstrating the role of CA in wheat-based cropping system, where we have to depend on crops which are more sustainable, like legumes that you have mentioned from Turkey. Next presentation we have is of Dr. Vladislav Minin from Russia. He is a soil scientist and agrochemist by education from the Leningrad region. He is working as a research scientist at Institute for Engineering and Environmental Problems in Agricultural Production in Federal Scientific Agro-Engineering Center. He's also coordinating a few projects on environment-friendly, smart organic agriculture to save environment and have clean water to Blue Baltic Sea. He has been Executive Secretary of International Association on Mechanization of Field Experiments and is also currently the Vice President of this association. So, Dr. Vladislav, floor is yours.
Yes. So you see this presentation? I tried. They don't want to sue me. Okay. So, dear Chairman, dear participants of the meeting, I would like to present this result of our research concerning legumes and other crops that are fixing nitrogen. So next. So the problem is that the intensive agriculture leads to the reduction of the humus, organic matter, and nutrients content in the soils. And field crops receive nutrients only from synthetic fertilizers. At the same time, conditions of many natural plant species are deteriorating in agriculture ecosystems, and greenhouses gases are increasing. So next. The biologization of agriculture as a system of interrelated measures provides sustainable pathways to enhance the productivity of food, animal feeds, and so on. And what we see is that ensuring balanced circulation of organic matter and nutrients, introduction of crop rotations with maximum proportion of high productivity crops, environmentally safe use of all types of organic and mineral fertilizers, increase the biological activity of soils, promoting of soil conservation technique for tillage, widespread use of biological and physical methods for controlling weeds, pests, and diseases. So next. We carry out long-term studies on sandy and coast loam soils, podzolic soils in Vladimir region. It is in the central part of Russia. What it demonstrates? It evaluating different legumes results shows that the total biomass of above ground and roots of perennial legumes amount of 1.7, 18.5 ton of dry matter per hectare, on which nearly half is root residues. On average, 6.3 ton of dry matter per hectare per year, and 131 kilograms of nitrogen was left in the soils with root residues and perennial legumes. Red clover has the highest nitrogen fixing capacity, as well as perennial lupine and yellow millet. So next. Next. So this is a table where you see different crops, what amount of nitrogen fixations we can see, coefficient of nitrogen fixations, and average nitrogen fixation per kilogram of nitrogen per hectare per year. So the most nitrogen fixing crops, this Lucerna, fodder, Galega, then foin. So next. Legumes are cultivated in crop rotations of non-Chernobyl zone of Russia, both as independent crops and as a green menu. General results of the long-term experiments shows that it is needed to have nearly 40% of legumes in the soils and for all crops. So next. So on this table you see what proportion of legumes in crop rotations and what they produce yield of crop rotations. So best variant, this is 40% of legumes in crop rotations. So next. Comparison of different fertilizer systems were conducted on the long-term field experiments from 1964 on sandy subsoil soils. Organic, mineral, and mineral fertilizer systems were aligned in amount of nutrients equivalent to 10 or 20 tons of farmyard manure per hectare per year. On average of 46 years, the efficiency of organic fertilizer system compared with organic mineral was lower by 39% and compared with mineral fertilizers, artificial fertilizers, by 34%. The total productivity of the crop rotations under the organic fertilizer system decreased by 15%, and according to the annual crop rotation, under the transition to organic fertilizer system amount to 0.49, 0.63 ton of grain units per ha. So next. So this table presents effects of different fertilizer systems on productivity of crop rotations of sand, loam, soils. So, and you see it is needed to apply manure and not big amount of artificial fertilizers to receive good results. So next. Different crops reacted differently to changes in mineral nutrition. Where there are no significant difference in yield between fertilizer system in the case of annual lupin, the shortfall in the wind-to-wheat harvest with switching organic fertilizer system reached 9%, for potatoes 13%, and for barley from 22 to 27%. So next. And it is very important to have a good nutrient content of organic fertilizers to apply for our crops. Organic fertilizers with high content of mineral nitrogen should be used for cereals, including litter and litter-free manure, peat and poultry dung compost, and so on. And you see that if you use poultry dung compost with litter and without litter, so we have a good results in content of mineral and organic. So next. It is possible to increase availability of nutrients or organic fertilizers for root zones by local introduction into the root zones. This means increase the crop, reducing their consumption by weeds and consolidations in unavailable forms, and thus increase the efficiency by 30 to 40%. This is especially affected with peat manure compost, green manure, and farmyard manure that have a low content nutrients in mineral forms. In field experiments, local application of organic fertilizers eliminated the deficit of deficit of mineral nitrogen during the first half of the growing season, and increasing the yield of corn compared with the broadcast application by 4.6 tons per hectare, or 18%, and of potatoes, but 47%. So next. Now in this table you see the influence of application methods on organic fertilizers on the yield of potatoes. So you see that the best is to use these organic fertilizers locally. So next. Next. Nitrogen reserve in agricultural soils can be significantly increased through the use of preparation of non-symbiotic and fixing microorganisms and other microorganisms. Along with nitrogen fixation, rhizosphere microorganisms produce physiologically active substances that stimulate plant growth and development. Recently, new strains of microorganisms have been identified that can suppress the development of pathogenic microorganisms. So next. The comprehensive research concerning biological cultivation on the crops began in 2016 in the field crop rotations at the experimental farm as located near the Lingard region. The effect of three groups of factors are studied. The level of mineral nutrition provided by the compost prepared industrially from poultry manure. Additional biological nitrogen provided by the introduction of nitrogen fixing microorganism, Flowbacterium. Biological fungicide, cartafin, based on basic subtiles. And the potatoes were treated by bee preparations during planting and during the growing seasons on the leaves. And the weeds were removed by special technique. So next. Due to the high level of soil fertility and enough water supply, even in the absence of the use of compost and plant protection products in the control variants, the yield was not a small enough level to 20 tons per hectare. The use of compost made it possible to raise it to 25.88 tons per hectare. Nevertheless, the infection of potatoes with various diseases in this way was high. Flowbacterium, which promote both the development of soil nitrogen fixation and the improvement the general physiological state of potato plants, provide a significant increase in yield to 2.62 tons per hectare, even without the compost. The use of compost, together with the Flowbacterium, increased the yield by another 4.46 tons to 27.33 tons per hectare. The use of compost together with pesticide cartafin give a yield increase of 9 tons per hectare. The maximum yield of nearly 31 tons per hectare was achieved with the introduction of an increased dose of compost together with cartafin. So next. So in this picture shows that effect of compost, effect of bow preparations on the yield of potatoes, standard tubes. So the maximum, you see that this is near 30 tons per hectare. So next. And this is conclusions. Biologization of crop production with its correct use allows us to get competitive products and significantly save the use of mineral fertilizers and pesticides. First of all, it is necessary to properly prepare and use organic fertilizers. They not only provide plants with nutrients, but also increase the carbon content in the soil and increase its fertility. As a part of crop rotation, it is necessary to have a sufficient number of fields with legumes that reclaim the soil and after row crops and enrich it with nitrogen and organic matters. The use of appropriate biological products allows us to improve the mineral nutrition of plants, protect them from diseases, and improve the general conditions of the crops to improve their health. So next. Oh, thanks for your attention. That's all.
Thank you, Dr. Vladislav, for very interesting results that you have presented based on long-term experiments and the role of organic fertilizers and also the involvement of legumes in the cropping system. Next presentation we have is by Dr. Yashpal Saharawat. Dr. Yashpal Singh is currently the country manager and principal scientist with International Fertilizer Development Center. He had earlier headed the national program in Afghanistan for ICARDA for almost more than 7-8 years. And he is actively engaged in conservation agriculture work, and earlier he was a senior scientist at Indian Agriculture Research Institute, New Delhi. He is PhD from University of Hohenheim in Germany and has wide experience relating to working with farmers on conservation agriculture. So Yashpal, floor is yours.
Thank you, Chairman, sir. A very good morning to all the presenters and the participants. I would like to join my colleagues in thanking the organizers for providing this opportunity to the IFDC to present their work on innovative fertilizer and fertilizer management technologies in the conservation agriculture based systems. It is evident that the food systems are the major drivers of the climate change, the land use change, the depletion of the natural resources, the freshwater resources, and the pollution in different ecosystems through the excessive use of the nitrogenous fertilizers and the phosphatic fertilizers. If we take an example of the green revolution, which is one of the biggest success stories in the agriculture sector till now, and from that one also, if we take example from India only, that in the past 5 decades, the food grain production has increased almost 2.6 times with a meager increase of 1.2% in the land use area, but the fertilizer use has increased by almost 13 times in the region. And if we think about the future, the global population is expected to be 9.9 billion by 2050, and the environmental effects of the food systems, they may increase by 50 to 90% in the absence of these technological changes. And these technological changes, specifically if we talk about the fertilizer, which is having a big impact on the soil health aspects. So we need dedicated mitigation measures reaching the level beyond these planetary boundaries. And we all know that there is not a single solution to these problems. There has to be a layering of the technologies, synergies and combination of the technologies, and those to be intermingled together to stop these increase in the environmental pressure. And if we take the examples on the fertilizer sector from 2 different countries, that is, one is developing country like India and the another one from the US, both the countries have almost similar acreage under the cereal crops. But on the right hand side, if you see that in US there is more judicious and balanced use of fertilizer, so using less fertilizer in the cereal crops, they are producing almost more than 100 metric tons of the cereals, and with the factor productivity almost more than 46. Whereas in India, the factor productivity, that is the amount of cereals produced per kg of nitrogen, are below 30%. So whether we are talking about the sources of the fertilizers or the technologies of the fertilizers or the methods of their management, that has to be improved, or we need to improve the application of the fertilizers. So that's a big question. And if we see the examples from India only, the current around between 30 to 50%, And on an annual basis, India is having an annual subsidy of almost $13 billion US. And if we see at the current rate of nutrient use efficiency, almost 77 to 8 billion of that one are going as a losses. So the question is whether we should go for a incentives to the technologies or we should go for a subsidy-based systems. And when we talk about the new production systems which are being propagated to enhance the soil health, to improve the productive capacity of the soils, and to have a sustainable intensification and go for a efficient natural resource base, these technologies like conservation agriculture, regenerative agriculture, or sustainable intensification. So all these technologies are being propagated on a larger scale. And when we talk about the conservation agriculture based systems, we are diversifying our rhizosphere totally because we are having a residue load of 5 to 7 tons on the soil surface. There is no tillage system. The water dynamics changes, and in overall, if we see the physical, chemical, and microbial changes are there, and my previous presenters has already discussed on those aspects, so I will not go into details of those. But under such a system, whether we should fertilize the soil or we should fertilize the crop, that's a big question. So how to manage the nutrients under these changing scenarios? So IFDC is working on a 4R concept for the conservation agriculture based systems. That is the right source of fertilizers at the right rate. This has to be applied at the right place. Normally, as on today, we are just broadcasting on the soil surface. And what is the right time for application when we are changing the rhizosphere totally? And in the next few slides, I will just give only 2 examples from the IFDC work. And first of those is the fertilizer super granules, that instead of having these traditional water soluble fertilizers, can we change these fertilizers into the brackets or the tablets of different sizes for different crops, different cropping systems, and different agroecologies. So on the left hand side, if you see, that is the traditional method of the farmers of the fertilizer application, which leads to more volatilization losses, nitrous oxide losses, more leaching, and more greenhouse gas emission, and the secondary problems of the soil health, whether it is acidity or other, and it also leads to groundwater pollution, and the system overall is less efficient, and it also reduces a subsidy also. Whereas on the right hand side, you can see that these prilled fertilizers, they can be made into the tablets in a particular NPK ratio, and even the micronutrients can be mixed with this one. So in a one go, we can give the complete fertilizer dose, and in a mechanized way for different kind of farmers, whether it is maybe handheld, self-propelled one, or for the bigger farmers, we can go for the planters also. So seed and fertilizer placement can be done as a one-go operation. And some of the studies that we have conducted, just here you can see the example from the maize crop, where we had 2 different cropping systems, the conventional tillage system, the agriculture system, and we used different sources in both the systems. First was the fertilizer application as recommended by the state agriculture universities, then what the farmers are using, then slow release fertilizer, and also these fertilizer deep placement through these brackets. And the results of this study showed that when we go for these brackets as the fertilizer deep placement, it improves the maize yield by almost 30% from the state agriculture recommended dose, by more than 50% by the farmers' practice, because farmers normally apply more of the urea as compared to these other fertilizers because of the subsidy part. And when we talk about the nitrogen use, it is reduced by almost 17 to 90%. That is almost 20% from the recommended one, and almost 45% what the farmers are using. And when we compare the 2 tillage systems, the conventional as well as the conservation agriculture, the benefits of this fertilizer deep placement were almost 24% higher in case of the conservation agriculture systems, where we had both the yield increase was there as well as the nitrogen use was less. And we also tried different kind of practices under both the conservation and this conventional system. We had the broadcast system of the fertilizer, we had the band placement, we had these brackets, we had the foliar spray, and the fixed application in the wheat crop. And our results here showed that when we go for a 50% of the deep placement of the nitrogenous fertilizer and rest application by the green seeker in the conservation agriculture based systems, the wheat yields improved by almost 20% and the fertilizer use was reduced by almost 22%. If we compare the conventional to the conservation agriculture systems, again, the nitrogen use in the conservation agriculture system was almost 12% less than the conventional system. So overall, this when we compare all these three systems, 33% basal, 50% basal, and 80% basal, we found that the nitrogen application, it can be reduced by almost 20 to 25% when we go for this bracket deep placement, and the wheat on an average, it's improved by almost 18%. We conducted several different experiments and at the farmers field and in the research stations with the cereal crops, with the horticulture crops, with the vegetables in different agroecologies of India. And here we find out that when we go from different agroecologies to new ecologies, the yield improvement in different crops, it is almost from 11% to 30%. And the fertilizer use specifically of the nitrogenous fertilizer, it can be reduced by 20 to 30% easily in different agroecologies. The second technology is about the layering of the technologies. When we go for a conservation agriculture based system and layering it with the subsurface drip irrigation system and in a CA based system. So here we can clearly see that in the conventional rice wheat system, which is a major cropping system in the northwestern parts of India, when we go for the subsurface irrigation system, there is a clear-cut yield improvement in the wheat crop, and in the rice it may be lower, but on the system basis there is almost half a ton increase in the yields when we go for subsurface irrigation system with the conservation agriculture based system, and also almost 60% reduction in the wheat water use. So efficiency of water is improved, efficiency of fertilizer is improved, and we are getting higher yields. And when you diversify the rice wheat system to the maize-based system, from the flood method to the subsurface irrigation method, there is almost a reduction of 40% in that one. But when we compare it to the flood system in the rice wheat to the maize wheat system, we can reduce it by almost 1/9. And this technology is having a lot of potential, being adopted only on 8 million hectares of area, whereas we have a potential of 50 million hectare area. So we can have this layering of technologies, the conservation agriculture based systems, the fertigation system, the nutrient management and the water management, and all these systems can help to improve not only the productivity also, but the income of the farmers as well as save our natural resources. We also conducted a study on the greenhouse gas emission under these two different methods, that is broadcasting of the nitrogenous fertilizer and the deep placement of the nitrogenous fertilizer. And on the right hand side graph, you can clearly see that the peaks of the red one here is that there was split application of the nitrogenous fertilizer urea at these times, and there were peaks. But when we go for the fertilizer deep placement or the nitrogen deep placement by these brackets, there is no peak, and the nitrous oxide emission is reduced by 60 to 80%, as well as the ammonia is reduced by 60% in these systems. And this technology is being widely adopted at a larger scale, and it is showing at the national level its impact. And in Bangladesh alone, we can say that this technology is being adopted by almost now 3 million farmers in almost 1.5 million hectare area. And on an annual basis, the Bangladesh as a country is able to save almost 120,000 metric tons of urea and producing an extra of 860,000 metric tons of the rice. And we conducted a survey of almost more than 10,000 farmers that clearly showed that there is a yield improvement when we go for the urea brackets by almost 15-20%, and the fertilizer use is reduced by almost 30 to 35%. This technology also provides a rural entrepreneurship, and the youth in the educated youth of the rural sector, they can take it as an entrepreneurship. They can make these brackets and just provide to the farmers. So it is a rural entrepreneurship model also. But what next when we go for the fertilizer research part? And if we see overall the research and development investment in the fertilizer sector, it is very less. If we combine the seed sector, the irrigation sector, the agrochemicals, and the sale of all these sectors combined is still lesser than the fertilizer sector, which is more than $300 billion at the moment. But the investment in fertilizer sector, specifically in the developing world and the underdeveloped world, is almost negligible. And second is that we are going for the new systems like conservation agriculture, regenerative agriculture. Under such systems, the nutrient management will further change from the traditional one. We need new sources, we need new molecules, we need new placement methods. And so we can say that at the moment, there are 3 pillars of conservation agriculture. The fourth one can be the efficient plant nutrition management. And when we take this as the fourth pillar, a lot of research work has to be done. A lot of investment has to be brought on that one. So what we need for that one is we need the dedicated fertilizer research institutions in the developing world. We need specialized education programs in the fertilizer sector. In the future, we need the incentive-based fertilizer policies, then the subsidy-based, and also link it to all these new systems like conservation agriculture, regenerative agriculture, or the sustainable intensification. So that's all from my side, and thank you for providing me this opportunity. Thank you very much.
Well, thank you, Yashpal, and I hope all participants are aware that he is also a rapporteur for this session. So we appreciate your presenting a paper as well. With this, now we have only a few minutes left for maybe 2 or 3 questions, quick questions. So far, I don't see in my chat box any specific question asked by our participants, but if someone would raise hand, we could possibly take 1 or 2 of those questions, or else we would like to conclude, because we would not like to take more of your time from the coffee break, which is due in next 10 minutes, I suppose. And
so there are two questions and one suggestion on the web. It's coming on the website. I'm not sure if it's coming on the website. Maybe
could you raise those questions, one or only those 2 questions, and quick answer by our current speakers, and suggestion can be circulated. Okay.
Okay, sir. So a question has been asked by Dr. Ahmed, the principal agronomist with Summit to Ahana, and he is asking, what do you mean by the intensity of conservation agriculture? And there is another question to Ahana from Imran, and he's asking, among the 3 options of experiments, which one had the highest soil humus content? And the last question, the third one, is to me from Sarah, and she is asking, how do you manage phosphatic fertilizers in conservation agriculture, and how do you incorporate in the soil? So maybe Ahana can go first if you allow.
So Ahana, you have to be very brief, maybe just 2 minutes, please. Answer quickly.
Sorry, some network problem. Can you repeat that for me?
Ahana, what do you mean by intensity of conservation agriculture? In your treatments, in the results, you mentioned that as we intensify the conservation agriculture. What do you mean by that?
So actually here we have 3 different treatment levels, that is CD, conventional tillage, and reduced tillage and zero tillage. And here also we have different level of residue incorporation, like 0% residue with some nutrient combination like 50% and 100% residue. So we have arranged it like in the level of residue incorporation, like 0% residue with 100% NPK, and we have graded it like 0% residue at the lowest level of intensity, and then as the highest level of intensity we have marked the 100%. That 100% residue is 75% NPK. So with the level of intensification, here we try to mean with different grade of tillage it differ along with the nutrient and combination.
Okay, and second carry from Dr. Amelzad is again that why the soil organic carbon will decline in the initial year. It should either be improving or it should be same, but why it will reduce? Can you give the reasons for that?
Yeah. Sir, maybe our climate may be the reason for that, because it is a subtropical climate, and initial years maybe that impact, because here I have presenting only our first year of practices, so the system is not mature enough to show the reflection, so it may be the reason, sir.
Okay, and the third one is among the three options of this experiment where the soil humus content increased. Do you have that data?
Sorry, sir?
Soil humus content.
Well, I think this can be taken up later, or she can answer directly to the person who has raised this question. As rapporteur, Dr. Yash, you can communicate to her.
Sure.
I would therefore like to take and conclude this session by just making few comments. One is that no doubt conservation agriculture is a technology which need to be scaled, especially in Asia, where the progress, except Australia, is not as much as one would expect as it has happened elsewhere. And if we have to accelerate use of conservation agriculture, probably we will require an aggressive approach. Secondly, conservation agriculture is the only scalable innovation for making the green revolution evergreen. So all the second generation problems of green revolution relating to soil health or water or environment can be addressed if we look into the conservation agriculture as a real good option. And this is win-win. It would require effort of scientists to work with the farmers. So farmers' participatory approach, as was indicated by some of the speakers, and also it would require the adoption of technologies, which would mean no dilution of dissemination of knowledge when you transfer it to the farmers. Otherwise, it can be counterproductive. It would require involving legumes in the cropping system for better sustainability. That's another important message which has come from these presentations, and it is a win-win situation. It would require mechanization of the kind which is more suitable for small farm holders. In Asia, the farm size is very small, of more than 80% farmers less than 2 hectares, and cropping intensity is also very high, and therefore what could be done to improve the soil health while having sustainable cropping systems. And we will have to replace or change the cereal-based cropping system and bring in legumes in place, as had been the practice in US and Brazil and other countries where you have crop like corn and soybean. And this was also demonstrated in Central Asian work by ICARDA and also by work in Russia very clearly, that you require a cropping system which is more sustainable. So we have that. Another aspect which came up very clearly was that we have to lay great emphasis on for future. One message very clearly came out that for conservation agriculture, you would require long-term experiments. That's what is the critical need, and it is costly. Not many institutions have long-term experiments, and there is definite need to lay greater emphasis in that respect. We will require on farm mechanization for placement of nutrients, even for fertigation and micro irrigation. So new approaches, and weed management is also another important area which has to be studied while we go in for conservation agriculture. There are good achievements. I must compliment all the speakers for highlighting many of these important points. And when I talked about farm mechanization, small farmers may not be able to own them. So custom hire services approach would also be necessary if we have to scale it. In Asia in particular, I'm talking, are from Asia to a greater extent. And the small tractors which are invariably in use would require different equipment than what was demonstrated, that in conservation agriculture, you have large machinery and horsepower of more than 50 to 100 horsepower tractors to run them. And you would need also the manufacturers who are effective, and these machineries are available locally to the farmers, and maybe farmers cooperative or farmers self-help group for custom hire services would be necessary. Having said all this, I would say this had been a useful session. We need to now see how we can accelerate the growth of area under conservation agriculture in Asia in particular. The achievements are significant in the rest of the world and mainly in the dryland areas. But in Asia, most of the work which we see is related to irrigated cropping systems. So what about dryland system? And how can those experiences be translated from other countries where it had been mainly practiced in dryland areas to our conditions? So I would like to say that it had been a useful session, and I would like to thank all the speakers and especially to the rapporteur, and also to all the participants who are with us this morning. Thank you very much.